Okay, so what we have going on in that electrochemical cell is we have at the anode, we have a reduction reaction taking place. Or I'm sorry, oxidation reaction taking place. So that's going to be the zinc solid making zinc 2 plus 2 electrons. And then at the cathode, that's the reduction, right? We have Cu2 plus 2 electrons going to Cu solid like that. Now, what if we wanted to know, like, what is the delta G of that reaction? I mean, how would we go about figuring it out, right? And normally, we go to the standard thermodynamic tables at the back of the book, and then you would go ahead and you would say, well, what's the free energies of the products, and subtract the free energies of the reactant, and then we get the free energy of the reaction. So what they do in electrochemistry is instead they do something similar, but they use voltages because that's sort of like the native language of the reaction. Electrochemical reactions are measured in voltages and in currents, that is, electrons that move through the reaction. So just to give you an idea, and I sort of made this funny slide. It's like it almost doesn't make sense to me anymore, but I'll explain it to you the best I can. So what we do in electrochemistry is we've decided to call this half reaction 0 volts. Okay? And so what we do is we set that half reaction up in its own half cell, like this one, and this is what it looks like. It says, I'm pumping in hydrogen gas. Now this is at 1 atmosphere because it has to be a standard states. So it's 1 atmosphere of hydrogen gas coming in, and this is 1 molar H plus. And so what's going on in this reaction is you have the reduction half cell that looks like this. H2H plus, which you could do as hydronium if you wanted to as well, but 2H plus 2 electrons makes H2. And this is going to be the gas. So that's the standard reduction potential for this particular reactor, standard reduction reaction for this particular half cell. And we define that as 0 volts. And then what we do is on the other side of this, we set up another half cell. And what we do is we measure the potential relative to hydrogen for all the other half cells. Now, they don't always set up the hydrogen electrode, I should say. And the standard hydrogen electrode, by the way, gets this abbreviation She. I'm assuming that's going to go out of style at some point, I hope. Anyways. So they take the standard hydrogen electrode and they measure all the other potentials relative to that, or they measure the standard reduction potential of hydrogen relative to another reaction, what they can use as a reference as well. So it's not that you have to set up the standard hydrogen electrode for everything, but we need to know at least what are the standard reduction potentials relative to hydrogen, and then we can calculate what those other ones are relative to hydrogen. So having said that, okay, we have this, I call it a cliffhanger, right? This guy's happy because this is the hydrogen electrode. It got picked as a reference. So everything else is relative to hydrogen being 0. So that means this reaction, let's say we have voltage going in this direction, right? This guy's somewhere on this electrochemical scale. He measures at this voltage. And this is maybe another reaction at this voltage. And if you wanted to, and this is how it works with voltages, if you wanted to calculate the energy between this guy and this guy, all you would have to know is, oops, that's not where I meant to put that, how much energy this one is above hydrogen and how much energy this one is below hydrogen, and then you can calculate it. On the other hand, it could also be that you wanted to know this one, but I think you can visualize how this happens. If I have this energy from here, let's call this 1, 2, and 3, from point 1 and point 2, right? If I have the energy, but that's the energy I want, but I know 1 to 0 and 2 to 0, then all I have to do is take the difference and I'll be able to get that energy difference between 1 and 2 there. So this, like we do free energies or enthalpies, we always have something we refer to as zero. That's the standard, the reference form for each element, or all the elements. For electrochemistry, the one reference value we have is hydrogen ion, and we set that to zero. Just like in free energy, the free energy of formation, for example, O2 gas is also zero. So it's the same concept. And then we can measure relative to that being zero. All right, so this is a little bit more of what I just said. Every redox reaction cell is the joining of half cells. So we're talking about the oxidation half cell and the reduction half cell. And we write out standard reductions based on their voltages relative to hydrogen, and we use the thermodynamic standard state when we do this. So this is 1 atmosphere for gases and 1 molar for things that are dissolved in solution. Now, and temperature, again, in the thermodynamic standard state is not part of the standard state. It's just the molarities or concentrations, for example. And then what we do, instead of listing free energies, right? We list voltages. We measure those using what's called a voltmeter, but we list the voltages of those half cell reactions. Now, this would be fairly useless if it wasn't directly related to the free energy of a reaction, and so in fact it is related to free energy, and this is the relationship that we use to convert between free energy and voltage. So let me explain to you really quickly what these different variables mean and how this conversion works out. Okay, so one of the fundamental unit relationships is that when you take the unit of charge, a coulomb, and you multiply it by the unit of potential, electrical potential, that gives us joules. So a coulomb times a volt gives us joules. Now, think about an electrochemical reaction like this one. I have Cu 2 plus 2 electrons makes Cu solid. Now, when I'm looking at C times V, right, how does it relate to this reaction? And indirectly, this is how it relates. The unit for charge that a chemist know is the electron. The unit of charge that the physicist knows and the electrochemist know is called a coulomb. So in this reaction, I have 2 electrons, right, per mole of reaction. So there's a term for that. It's called equivalence, and it's just 2 EQ for this reaction, or you could say 2 EQ per mole if you want, but it's the amount of charge, the moles of electrons for this reaction. And then Faraday's constant is the relationship between the unit of charge, 96,485 coulombs, for every mole of electrons. So this is actually per equivalent. So when you take a look at how this part of the math works out, what you're doing basically is you're saying, well, if it gives me 2 electrons every time this reaction runs, then it gives me this many coulombs of charge. And if you know the voltage for that reaction, you can convert that over to free energy. So this NF is this part here. So let's apply this relationship to the free energy of the Daniel cell, the zinc copper electrochemical cell, which we're looking at up here. It's the Daniel cell. When you measure this voltage, it's actually 1.10 volts. And so it says here, this is delta G is equal to minus NFE, right? We're going to calculate delta G of the reaction and then determine whether or not the reaction is spontaneous or non-spontaneous. And we'll do it in kilojoules. So N for this reaction is 2. And I get the 2 from the half reactions I used to put it together. So this number that I'm using here, this 2, is the number in the balanced reaction. So if the balanced reaction, let's say this was 3 and 2, and you had to cross multiply and you get a 6, let's say, for example, then N would be 6, okay? But it's for the balanced reaction, however you have it balanced. So I'm using 2 in this case. So I have delta G is equal to negative, and then it's going to be 2 equivalents times 96,485 coulombs per equivalent times 1.10 volts. And then the equivalents will cancel out, and I'll get joules. And that comes out to be negative 2.122, 3. Let's do 3 times 10 to the 5th joules joules of energy. Now, in terms of kilojoules, I just converted over to kilojoules. It'll be 212 kilojoules of energy for the reaction that's shown in this reaction. So this is 212 negative kilojoules. Okay, and we get that by measuring the potential of the cell from the anode side, this side to this side, which is literally take this voltmeter, we'll say 1.1 volts. Okay, so I've been talking about standard reduction potentials. I want to show you the standard reductions table to you. And unfortunately, like normally in class, I hand these out and then I can like point at them and you can see them in class, but I think this might work just as well. So standard reduction potentials are all relative to hydrogen being measured as 0, so you can see that down here. And I can move that up and kind of zoom in on it a little bit. That's what we're measuring relative to 0. Now, if you want to do an electrochemical reaction, you have to have both a reduction and you have to have an oxidation. So let's say we were looking at earlier silver. So this is silver ion. It has a standard reduction potential of 0.8 volts. Now, the other side of that was a piece of copper wire, and it was going to copper 2+. And you'll notice that the standard reduction potential for copper 2+ is 0.34 volts. Now, the difference in voltage between these two, right, can be calculated by going like this. Oh, I lost my silver. Starting from here, just remember I can't write on this, and subtracting the voltage it takes to go from here for the copper to a reaction. Because relative to this reaction being 0, the difference in energy between the silver electrode and the copper 2+ and the copper electrode is 0.34 volts subtracted from 0.8 volts, right? So that voltage difference is what is the voltage for that particular reaction. Now let me write that out and we'll look at it in a little bit more detail. So I want to make sure that you understand what I'm about to show you is different than how the book does it. So I don't want you to get confused. But what we're going to do is we're going to figure out which way this reaction is spontaneous. Now, you notice these are both written as reductions. And so what I'm going to need to do is I need to have a reduction reaction and an oxidation reaction. Now, when we watched the video, if you remember, the video showed silver solid being formed at the copper surface. So we really know already that this is written in the direction of the spontaneous reaction. But since this is a reduction, this one has to be written as an oxidation reaction. In other words, I have to flip this reaction around. And so I'm going to flip it. I'm going to write it out like this. Oops. Cu 2+, I'm sorry, Cu solid goes to Cu 2+ plus 2 electrons. Now, since I flipped this reaction around, the voltage that it represents is actually minus 0.34 volts. I think my screen's dirty. 0.34 volts like that. Negative though, because I flipped it around. Just like delta G's, right? Or delta H's. When you flip, when you flip a reaction around, you change the sign. Now, this reaction, right, I need to double it. And it's going to be Ag plus, right, but I need two of them, plus 2 electrons. And that's going to be giving me Ag solid like this. Now, you would think that you would double the voltage, but you don't. It's going to be 0.8 volts. And I'll explain that to you in just a second. So when I add these two together, then what's going to happen is, for the spontaneous reaction, what I'm going to get is 2 silvers plus Cu solid. The 2 electrons cancel, goes to form Ag solid plus Ag solid plus Cu2 plus. Remember, that was the blue that we saw forming in the solution. Now, just like free energy, so this part's the same as the free energy. When I add 2 reactions in order to get the free energy of the reaction, all I have to do is add these 2 together. So I'm going to flip one reaction, that was this reaction, and change its sign and add the 2 together, and I'll get 0.46 volts. And remember what we said before, if the voltage is positive, then the reaction is spontaneous, because that means a negative free energy. Okay, so the process is this then. If you want to know the voltage of any reaction, okay, then what you have to do is you have to find the 2 half reactions, and then you're going to have to flip one of the half reactions to match whatever reaction you're looking for. And then when you do that, you change the sign, and then you add the voltages together. So if you double it, like I did for the silver, you don't mess around with the voltage. But if you flip it, you still have to change the sign. Okay, so that's the process. So let's talk a little bit why you don't have to mess around with the doubling of the voltage when you double the reaction. So what you have to remember is the relationship between the voltage and the free energy. So delta G is equal to minus NFE. And the electrode voltage, if you solve it this way, is minus delta G over NF, like that. Okay? So really what we're doing here is we're doing an addition of free energies, but we're using the relationship of the voltage to the free energy, not just the free energy. Now, what happens when I had this reaction? This reaction was, for 1 electron, it was 0.8 volts. Now, for 2, right, if I doubled this reaction, I had 2 electrons, you would think that this number would double. But notice what happens here. If I double the free energy by doubling the reaction, I also double the number of electrons. And because of that, the voltage doesn't change as you scale the voltage, or the stoichiometry of this reaction. So if I multiplied this reaction by 3, the voltage would still be 0.8 volts. So it's a little bit hard to grasp at first, but you get used to it after a while, that doubling reactions doesn't necessarily require you to change the voltage. Now, if it's the free energy you're talking about, yes, doubling a reaction doubles the free energy. But since the voltage is related to the number of electrons and the free energy, and they essentially are scaling together, right, there is no change in the voltage by changing the reaction.